When we're talking about three possibilities for intersections of lines or solutions of systems of equations, we're talking about two unknowns across two equations, because we're talking about lines and not planes. When we're talking about those three possibilities, we're talking about infinitely many solutions, or points of intersection. We're talking about no solutions, or we're talking about a unique solution. We need to sometimes engage with these things called parameters and parametric equations of lines. So parameter and parametric, you can hear the connection there. And so we've got this example, the simultaneous equations given there, they have infinitely many solutions. Now we can see why that is, because the second equation is basically a multiple of the first, so they touch in infinitely many places. All points, in fact, are common. So they have infinitely many solutions. So how do we describe them and make use of a parameter? First of all, I'm going to choose a parameter. I'm going to call that lambda. It's a common symbol used. So choose lambda as the parameter. And you need to focus on one of the two equations. I'm going to focus on this one because it's reduced down a bit more. And we have 2x plus 3y equals 6. Now we're going to say let y equal lambda. So that would mean that to get an equation, a parametric equation of x, which describes the line, we would need to go, once we've made that substitution, we would need to go 6 minus 3y over 2, which is 6 minus 3 lambda over 2. Now, being a parameter, lambda can be any real number. So x equals 6 minus 3 lambda over 2, where lambda is the set of all real numbers, is a parametric description of the line. So something like that's required if there's infinitely many solutions. You can see that domain will provide that. Okay, so here we have two simultaneous linear equations involving x and y. It's a bit abstract because we have an unknown m. So we have m minus 2 times x plus y equals 2, and we also have mx plus 2y equals k. So what we need to do is determine the values of m and also k such that the system of equation has firstly a unique, then no solution, then infinitely many. So this is basically applying our knowledge of the three situations. So I've written them down as simultaneous equations, and I'm going to solve for x first of all. So let's go to equation 2 minus 2 lots of equation 1 and see what that provides. So you can see that that would eliminate the y's, and we would have m, as far as the x's go, we would have mx take away 2 outside of m minus 2x that would equal k minus 4. So just going through, completing the rest of the steps there, we have x equals k minus 4 over 4 minus m, or if you prefer 4 minus k over m minus 4, where m cannot equal 4. So if we sub that result, which I've called equation 3, into 1, and also rearranging 1, which I've rewritten above. So rearranging, making y the subject, we have 2 minus m minus 2 times x, and subbing in for x, take k over m take 4. So expanding so we can simplify, we have the following. So we have 2m minus 4m is minus 2m, negative 8 minus negative 8 is 0, so the 8's cancel, so that one cancels as well. Then we have minus negative km, which is plus km, minus positive 2k, which is minus 2k. We could take k as a factor out, and we have k outside m minus 2 minus 2m over m minus 4 for k, for y, sorry. So we have an equation now for x and for y. So back up there, equation 3 is x. So maybe call this equation 4. So getting back to the question, part A, we have to find values of m and k such that the system equation has a unique solution. Now remember, when we say solution is xy, results for xy. So if we look at equation 4, provided m doesn't equal 4, and that's also true for x, provided m doesn't equal 4, and k can be any real number, so provided we will have a unique solution for x and y. So there are all the possible values that could lead to a unique solution. Okay, so parameter k and m just cannot be equal to 4, can be equal to everything else. So another way of writing that would be k would be element of real numbers but excluding 4, the set of all numbers excluding 4. K can be any real number, so they would generate a unique solution, all of those cases. So that was part A. Part B, okay, there'd be no solution if m equals 4. We can see that by dividing by 0 above. Moving up here, equations 3 and 4. So m can't equal 4, dividing by 0. So if we did sub in 4, we'd see we have a case where k could not equal 4 because we would have copies of the same line. So m can't equal 4. If it does happen to equal 4, we get these two equations here. Alright, and for subbing into the original equations, we get this. So there'd be no solution if m equals no solution if m equals 4. Now in this case here, k cannot equal 4, because if m equals 4 and k equals 4, we will have part C infinitely many. So let's write that down. So 4x plus 2y equals 4, and they're copies of the same equation. There's a multiple of 2, they are the same line. So There are various values of m and k. That's quite an abstract question.